Right. Welcome everyone. For this week's IQS seminar, we have Abhaya Seetaram from University of Rochester. Abhaya did his bachelor's and master's of science dual degree in from ISER, Thiruvananthapuram, India, and right now he is a PhD student in University of Rochester in the group of Gabriel Landi. For today's seminar, he will be talking about his recent paper on time-resolved stochastic dynamics of quantum thermal machines. Okay, the floor is yours.
Hi, everyone. Thanks for the kind introduction and also the invitation, Vivek. Today, I'm here to talk about some of the recent works we did. I'm a PhD student at the University of Rochester. I'm a third-year grad student. Today, I'll be talking about time-resolving stochastic dynamics, in particular of quantum thermal machines, and the fantastic machines and how to find them. Hopefully, I'll be able to convince what I mean by fantastic and some examples of it. This is based on a recent archive preprint that we put out, and the archive ID is given there. Can you see me? Okay. Well, the motivation for this work is, in general, trying to understand thermal machines in terms of stochastic dynamics. Usually, thermal machines facilitate exchange of heat and work, which is both forms of energy. And whenever we say thermal machines, we usually think of either an engine or a refrigerator. Can you hear me?
Okay.
Hi, can you hear me?
Yes,
okay.
we do.
Well, an engine, again, the aim of thermal machines is to transfer heat from one to the other while probably extracting or consuming work. In that sense, an engine extracts work while transferring heat from hot to cold, or a refrigerator does the opposite by consuming work. We can also have other examples of thermal machines, which are like heat pump or accelerator and so on. But the basic premise is converting one form of energy to the other, which is usually heat to work. And in terms of classical thermodynamic descriptions, the heat and work are almost thought of as continuous fluid-like quantities. But the recent advances in nanoscale heat engines suggest that we can also describe these kinds of thermal machines at the level of quantum trajectories. So in particular, what I'm thinking of is some sort of typical time traces one can have for, let's say, double quantum dot systems, or expressing stochastic dynamics of thermal machines in terms of these quantum jumps, or even building quantum trajectories for photodetectors. All of these have some sort of characteristic events that we can characterize as jumps, and then extract some physics out of it. And given this is the premise, or in concrete words, the premise is that we try to now think of energy exchanges between the system and the reservoir, not as a continuous quantity, but in terms of these discrete stochastic jumps. And these jumps can occur at random times and also in random channels. By channels, I mean different detection schemes that can give the information of when these jumps happened and what kind of jumps happened. And these channels can also probably characterize the different energy scales that each energy quanta might be exchanged with the reservoir. In particular, we can broadly classify these events into 4 channels corresponding to either an injection or an extraction from either of the hot or cold baths. And we envision that an experimentalist can have access to the data of jump detections along with the time tags of when they happened. So the typical scheme is you have a generic system that is sandwiched between a hot and cold reservoir. Maybe there is an injection of energy at some point, which is given by the symbol H. And if there is a subsequent extraction to the cold bath, then you might have eventually extracted work out. this is typically what's intuitively characterized as a heat cycle. But you can also do the reverse by consuming work and think of this as a refrigeration cycle. Notice that I'm also plotting, or I'm also having a scheme where I can detect these jumps at different times. So given this kind of a premise, what we try to understand then is can we ascribe some thermodynamic cycles to these kinds of jumps? Similar works have already been followed in the past, including our own Professor Andrew Jordan, who might be in the audience, I'm not sure, but uh, uh, where they have analyzed steady state thermoelectric engines for uh, three-terminal quantum dot setups, something to the tune of this. Uh, most of the time, what's being observed is the state of the system continuously, and then understand the statistics of cycles. A similar work that came out of Janine Splitz-Sorcer recently is also understanding the cycles at the trajectory level and then associating heat and work currents and also entropy production and so on. But specifically, quantum jump approaches to the microscopic heat engines is also something explored in the past. But our approach is slightly different, and I'll hopefully able to convince you how different it is. The main paradigm in our research is this. Is it possible to identify thermodynamic cycles solely from these strengths? For example, the first two bits of this might seem like IH and EC, which is injection from the hot and extraction to the cold, which is a work cycle or an engine cycle. But the next subset of strings might cause a problem. Why do they cause a problem? Well, let me show you what exactly I mean by cycles here. Given this kind of a characterizations of operation of a thermal machine in terms of these jumps, we can broadly think of these four kinds of cycles. The first two I have fairly elaborated, which is engine and refrigeration kind of cycles, but you might also come across these idle cycles where an extraction, an excitation comes from the reservoir to the system and it jumps back to the same path. In which case, there is no entropy produced, there's no heat transfer. None of the thermodynamic variables are the witnesses for these kinds of processes. So broadly thinking, what I'm thinking as useful is where some heat is transferred. It might not necessarily be the case that for an engine operation, a refrigeration cycle could be worse than an idle cycle, but in the broad classification of whether there is a heat flow or not, then these two constitute useful and the bottom two constitute ideals. So we are trying to then characterize the jump sequence you would observe in a classical detection scheme to give us some insights on the thermodynamics of the system. So in particular, while the first two letters are okay, what exactly happens to the next substring that I've highlighted is something I want to talk about before moving on to the statistics. In particular, if you observe them, there are two subsequent injections followed by two subsequent extractions. So this is a case of multiple excitations. And there are at least two ways to interpret this. One is the same excitation which was injected from the cold went back to the cold. So an injection from cold followed by an extraction to cold. And the same with the hot bath. So this could be a case of two idles. But if you group them in the other way, then this is a refrigeration cycle and an engine cycle together. Well, overall, there's no entropy production, of course, but one involves some heat transferred between the two reservoirs and the other does not. Since the excitations themselves are indistinguishable, there is no way to unambiguously classify these into the cycles that I just described. So multiple excitations do not, the question of how do you identify cycles just based on the symbols might not even be a well-posed question for multiple excitations. So at least in what follows, I'll stick to single excitation machines, wherein at most you can have one excitation or there's no excitation in the system, which effectively means that in terms of the jump sequences, the injections and the extraction events alternate with the trajectory. So this is a crucial assumption, and the single excitation assumption is where most of the math that comes in later. So the outline for the rest of the talk is going to be, given that we can characterize events into cycles, what's the probability of each of these cycles? Since we also have access to the time tags, can we comment on the statistics of how long does each cycle take? What's the average waiting times? And can we learn any physics out of the statistics? In other words, is there any physical observable that is tied to these statistics? And since idle processes do not really transfer any heat, in terms of transport, can we optimize idle cycles in favor of used ones? As is customary in thermodynamics to begin counting at zero, let me also ask a question, which is, for all these kinds of machines, what kind of equations of motion can we first write? What's the structure of quantum master equations? An example that I'll follow up with is the mostly used three-level Mason system. And let me begin with the first question, or the zeroth question, which is, what are the constraints on master equation? Well, if we were to assume that the system is weakly coupled to the reservoirs, then we are well justified in using a Markovian master equation of the following form, which is the Lindblad equation, wherein the system's evolution is given by a Hamiltonian part, which is the closed dynamics, plus the dissipation parts. And the dissipation thermal relaxation rates can be thought of as extractions and injection rates. And the dissipator will have two kinds of terms, which is an extraction operator or the injection operators. Why this is well justified, and you might say, where this follows Markovian equation, given that we are specifically dealing with single excitations, what more additional structure can we force on this kind of equations? Well, we prove in the article that I posted that if the quantum trajectory sequence must have alternating injections and extractions, then in a specific basis, which I'll explain later, the Hamiltonian turns out to be block diagonal, and the jump operators turn out to be block off diagonal, which can then be made into strictly upper triangular. And this is not an unexpected result or anything. It's just that the Hamiltonian and the jump operators complement their roles, so that the multiple excitations are not injected into the same space. Perhaps this will get more clear as I show an example later. But this turns out to be quite general, and one nice way of thinking about all this is trying to understand the dynamics in terms of two subspaces. As soon as you extract an excitation of the system resides in what's called as post-extraction subspace. And likewise, we define post-injection subspace. And what's nice about then the single excitation assumption is these subspaces cover the entire Hilbert space and they're mutually exclusive. So if PE and PI are the projections of projections onto these respective subspaces, then these are the two conditions that we want the operators to satisfy. And then we are guaranteed to have this Markovian equation describe a single excitation machine. And this goes both ways, and the proof can be found in the preprint. Good. So then what we would like to understand is how do we extract statistics out of this? And for that, we rely on one of the unraveling frameworks for the master equation, and specifically that is the jump unraveling framework. The jump unraveling framework is quite intuitive in the sense that it prescribes a treatment wherein you decompose the Lindbladian into either jumps or no jumps. And specifically, these jumps occur at random times. For these kind of operations we are considering, we could have 4 jump super operators corresponding to extractions and then injections from either of the baths. And every once in a while, these jumps happen, but when the system is evolving continuously, then it is dictated by an operator known as no jump operator. Well, so we rewrite the entire Lindbladian in terms of all the jump operators plus the no jump. And this scheme works quite well because of the following understanding, which is that what you see at the top is the solution for the Lindblad equation, which is if it forms a semigroup, you have e to the L dt rho. We can rewrite this solution in terms of effectively a non-Hermitian Hamiltonian followed by operators that describe the jumps. So H effective is the non-Hermitian Hamiltonian, wherein you take the entire Hamiltonian and subtract all the jumps. And up till the linear order, the third term in the equation above, which is of the orders of dt, represents the jumps. So in the measurement scheme, if you define the cross operators as given, m0 and mk, where m0 refers to the no jump and mk refers to clicks in certain detectors labeled by k, then we can rewrite the entire evolution in terms of these cross operators, which are also properly normalized up to the linear order. So this unraveling is quite intuitive in the sense we can decompose the whole dynamics in terms of almost no jumps with every once in a while jumps kind of description. We'll use the following paradigm to now understand the statistics. And before I delve deep into the statistics again, let me introduce another concept, which is the jump steady state. This is the steady state that is equivalent for the jump sequences, because what we're interested in is the long time steady state behavior of these kind of sequences. So we would like to input a state that keeps the sequence or the jump sequence stationary. And we find that the form of then the initial state should be something of this form, which is the rho SS is the assumed unique steady state of the dynamics, which is given by the Lindblad operator going to 0 anyway. And then the way we define jump steady state is we average over all the jumps and then normalize it. Averaging over all jumps takes care of the ignorance we have in terms of what dynamics is happening at the steady state. And the other fact is that this is the only thing that makes the jump sequence stationary. And the nice thing about single excitation assumption is we can then decompose this entire jump steady state in terms of these two subspaces of the Hilbert space, the post-extraction and post-injection, where PE and PI give the probability of then these jump steady states. But in particular, because of the block diagonality of Hamiltonian, it's also quite easy to deduce that these PE and PIs are half, 1/2. So, half, in the sense that the excitation spends equal amount of time in either of these subspaces. Because of the assumption we cannot have 2 injections in the in succession, the part that is pi I goes out of the window. So the convention is that we always begin with an injection. So if we begin all our cycles with an injection, we assume our initial state should be then on the post-extracted subspace of the Hilbert. So pi E is going to be our initial state. So now we are ready to explore the cycle statistics. In particular, let me first then extract the probability of each cycle. The reminder is that each pair of jumps then constitutes a cycle. And for each pair, let me denote the cycles with a random variable x, taking integer values. And 1 is engine, 2 is refrigeration, and so on, which is seen on the slide. Now what we're interested in is the time result probability of observing a given cycle X within a duration tau. And as is typical fashion, we write then Px of tau as the trace of some operator in the initial state by E. But this operator is what we like to call a cycle operator. And the cycle operator has the following meaning. So we begin in the jump steady state. In fact, the post-extracted part of jump steady state. And for maybe until time t, we don't discover any jumps at all. So it evolves according to the no jump evolution, which is the e to the L naught t. And by convention, our first jump is injection. This doesn't have to be the case. One can go the other way as well. So the first jump is injection. And then since the duration of the entire cycle is tau, the next jump must happen at the time tau minus t. So we evolve the entire state using no jump operator for tau minus t. And then the last jump will be an extraction. And then we take the trace out of this entire object to build probability distribution. But since we are only concerned with the durations, we can integrate over all the first jumps and get rid of t, which effectively implements a cycle of duration tau of the type X. Now, if X is equal to 1, then I would want the injection operator to be from hot bath and the extraction to be the cold bath, and so on. So the X decides the baths that are involved. This already gives us the time resolved probabilities. I'll show the examples later. And if we integrate over all the durations, then which will yield us a total probability of observing any of these cycles. In particular, it will tell us the operation of the stochastic engine, stochastic machine in general, in terms of engine cycle or refrigeration cycle, or even the times when it's doing nothing. That's just a simple integration. And for the sake of future slides, let me denote the inner operator that is in blue as OX, which is marginalized over all durations. Of course, this satisfies normalization, and this is quite general. We can prove this for single excitation machines, and the proof is over at the appendix of the article. Well, this prescription already gives us the probability. Then we can ask what's the average waiting time for each cycle. And these are all conditional expectations, because given that these jump events have happened, or given that the cycle has happened, what's the time at which these cycles must have taken? And that is usually, that's just the usual form, which is tau times the px of tau, and then you integrate over all durations. And then the unconditional average is also quite simply given by that. And in the article, we try to derive then an expression in terms of the jump unraveling framework. This equation might not be all that insightful because it doesn't immediately tell us anything. But the point of me putting this was just to show that the framework allows a neat expression, which is quite general for any case, as long as you can use the unraveling framework. Well, let me briefly also give some sort of connections to the full counting statistics, which is, if you think about it, these average waiting times must have some connections to the average number of jumps of the baths per unit time, which is usually known as the dynamical activity in full counting statistics. And in fact, it's quite simply given by a trace of all the jumps at the steady state. And this connection is obvious in the sense that average waiting time must be inversely proportional to the number of jumps per unit time. And we recover that. And for all single excitation machines, this holds. And E of tau is 2 over KHC. And this 2 precisely comes because each cycle involves 2 jumps. While this is no surprise, and in fact, this should hold true, this is just a nice sanity check that the unraveling framework fits in well for this. What's quite unexpected for us, or quite interesting, is we can then recover a physical observable, which is the excitation current, which is the current that is exchanged with the baths. It's self-explanatory that the current should be how how many do you extract minus how many do you inject at either of the baths. Because of the single excitation, again, there is a conservation law, which is why you can do it, measure at the cold bath or the hot bath, as long as you take care of the signs. So we can build excitation currents, and this excitation current is then tied to the statistics of jumps. And it might also look unsurprising at first, but the fact that these time-resolved statistics can yield to something as simple as measuring a current at the lab is quite interesting, because then we have a description at the nanoscale. So here, excitation current is P1 minus P2 over E of tau, where, just to remind you, P1 is sort of the forward current and P2 is like the backward current. And since we also know the E of tau is related to the dynamical activity, maybe there are opportunities to give a better bounds in terms of the excitation currents and define the fluctuations of these currents, both of which would then probably yield some connections to the thermodynamic uncertainty relations or kinetic uncertainty relations. Again, none of these facts are probably quite alarming at the first notice, but the fact that we are able to do it feels quite interesting. Now I'd like to highlight one of the interesting facts about all this dynamics, which is how regular is your machine? Or given that the machine can only transfer heat at certain intervals of time, how long does it spend doing nothing? In other words, how many idle cycles between two useful ones? And we can try to think of this metric in terms of either the number of intervening idle cycles between two useful cycles, or equivalently, how long did the machine spend doing nothing in between two useful cycles. We were able to find expressions for both of these quantities. They might not be, again, illuminating just to look at them, but the point is that this jump unraveling framework will allow us to compute these statistics and possibly also find optimizations for these in the end. And this will also encompass all sorts of correlations between cycles. For example, the presence of one useful cycle might influence an immediate observance of the next useful cycle, and then as in some sort of bunching or anti-bunching of useful or idle cycles. But these expressions already capture that. So if we were to calculate, let's say, covariance of any of these particular cycle times or cycle events, the intermittency, as in how regular is the machine, should already be captured in these two expressions. And the cycle operators have the usual form, and for the time, we take the Fourier transform and find something. Well, I'll show certain plots for these, and maybe these might be some might have some insights. One of the examples that people usually take is the 1959 Scoville-Schulderbois heat machine, and we apply that to our case, wherein our quantum system is this three-level maser, which is coupled to hot and a cold bath. Each of these have Bose-Einstein distributed populations. Since the hot bath is between level 0 and 2, then we would like to understand the jump operators for both the hot and cold baths, which I'll show in the next slide. And hopefully we'll be able to build cycles of this form and then analyze the statistics based on the expressions I just showed you. So the maser is governed by a time-dependent Hamiltonian, which is given as follows. So between 0 and 2, there is a bath. Between level 1 and 2, there is another bath. But between 0 and 1, you can have a time-dependent drive. And the usual description to solve these kinds of dynamics is to then go to a rotating frame and eliminate the time dependence. And for this kind of setup, what we find is the jump operators have this form. I forgot to mention in the slides that the sigma 02 and sigma 12 are simply just the transition operators. By that I mean sigma ij is ket I and bra j. And the relaxation rates, which involve injections and extraction rates, have the following form as well, with the bath populations taking Bose-Einstein distribution, with TH and TC being the hot and cold bath temperatures. Well, if you look at the structure of the Hamiltonian and the jump operators, their Hamiltonian is off diagonal only in the 0 and 1 subspace, and the jump operators are purely off diagonal or upper triangular. So we would expect then this, if you plug into the master equation, the Lindblad master equation, to allow for jump events that are alternating injections and extractions, as I showed you in the couple of slides ago. So given that we are good to go in applying our theories, let me show you time resolved probabilities for this. What I have is here we have chosen parameters in such a way that the hot bath population is more than the cold bath populations, in which case we would expect the cycles mediated by the hot bath to have more probabilities, which is exactly what we see. X equals 1 and x equals 3 are the ones that are mediated by the hot bath. The solid lines represent useful cycles and the dotted ones represent the idle cycles. And the wiggles that you see here are because of the Rabi oscillations between 0 and 1, the coherent dynamics between these two. And in the long time limit, these follow some sort of decaying oscillations, exponential times cosine. And this already gives us some insights into how should you operate your machine. If we then integrate over all times, then we'll see the exact regimes at which this stochastic machine operates as a refrigerator or as an engine, as a function of the gradient of the hot and the cold bath temperatures. We would expect the current, which is difference in the probabilities, to be proportional to the difference in the populations themselves. And this is what we observe if we compute the formulas for this particular example. And an interesting thing we found is the idle cycle probabilities in particular bound those of the useful ones, which we find it quite interesting because if you go to the refrigeration regime, then you find P3 and P4 bounding P1 and P2. And same in the engine regime, it's just that the inequalities change. So it somehow gives us the impression that it's almost always unlikely to always extract work out of this or heat out of this. So let me also show average waiting times. It turns out that for this particular model, whether it's an engine cycle or a hot idle one, it's the same waiting times. And I suspect this has to do with the fact that these constitute renewal processes, and it's particularly then simpler to think of these as classical stochastic processes. And then the average waiting times usually depend on how do you enter the subspace rather than how do you leave. Both the cycles, engine or the hot idle cycles, or in the same sense, cold cycle and the cold idle cycles, have this feature that they both depend on how do you enter a particular subspace, which is why the average waiting times seem to be equal. And if we go to resonance conditions, then all these conditional averages seem to have no differences at all. And the final fact I want to again emphasize is this discussion between efficiency and intermittency. The excitation currents that I showed you before are directly related to the heat and work fluxes of this machine. In particular, they take a quite simpler form here, which is hot bath fluxes omega h times IEX and cold bath fluxes omega c times IEX. Just a reminder that omega h and omega c are energies of the hot and the cold baths. The work flux and the heat fluxes add up to 0 only at resonance. Yeah. But if you think of efficiency then, which is the work divided by the heat input, then it ignores or the cancels out the contributions from excitation current altogether. So it does not give any indications as to how regular is your machine at all. So there might be another aspect to the operations of these machines that is not captured by efficiency. And we think intermittency is one such aspect. Just to showcase what do I mean by that. Well, if you were to think of intermittency in terms of how many idle cycles happen between two useful ones, we plotted this for the 3-level measure. And here it's quite simple because the cycles themselves are independent, and hence the useful cycles follow a geometric distribution. PU is in particular a probability of useful cycles, and 1 minus PU gives the probability of idle cycles. And if there are n idle cycles between two useful ones, after you normalize, you get something that's plotted there. In particular, we plotted mean and the variance of these intervening idle cycles as a function of the gradient of temperature between hot and the cold baths. Given our definition of what's useful and what's idle, it turns out that if we want our machine to be optimal, then we should operate at the temperature gradient that is equal to the energy gradient between the baths. In particular, the useful cycles also turned out to be proportional to the bath at the pump strength, which is epsilon square, and inversely proportional to the detuning and decoherence rate. But if you ask the same question in terms of how much time it takes to transport heat, then we get a plot something like this. In particular, one would expect that if the gradient between the hot and cold baths are too high, for example, TH is 10 times TC, then you would expect a faster heat transport, which is exactly what we observe as well. A high gradient would accelerate heat transport, but that does not necessarily mean that you're optimizing for idle cycles, because if you want to minimize the idle cycles, then the gradient TH by TC should be around 4, which is 4 is not a magic number. It's just the parameters I've chosen turned out to be 4. But in general, my point is that a faster heat transport does not necessarily mean you're suppressing the idle cycles. Well, I think I'm towards the end of my talk. Just to understand how do we go about a couple of future directions, this is one of the unravelings out of many unravelings possible for the master equation. And perhaps diffusive unraveling is one other thing that I'd like to try out. Exploring the concept of intermittency against efficiency is also something traditionally not discussed, and maybe there is some insight that we can get in terms of operating these thermal engines in mesoscopic conductors case is what I hope to achieve. And extension to models involving multiple excitations seems very exciting, but this does not readily generalize to anything that involves multiple excitations. So in conclusion, we established a structure for the master equation in place of single excitations. We analyzed the statistics and developed some figures of merit for intermittency that is quite distinct from what efficiency can capture. This work was done in supervision of Professor Gabriel Landy and also Patrick Potts at University of Basel, Switzerland. Most of the formalism is in the PRX quantum tutorial, and also I'd be happy if you can give me some feedback on the preprint we recently put out. Thank you. I'd be happy to take some questions.
Yeah, well, any questions?
Sorry, I'm unable to hear. Sorry, I missed.
Oh, you're not able to hear us? Are you hearing us now?
Yes, now I'm able to hear. Yes.
Okay. I can start with the questions. Do you understand why? Is there a way to understand why there is a switch of this this ordering between all the probabilities? I mean, is there a way to understand why like P3 and P4 are on the opposite bounds?
Yeah, that's a good question. So what we're trying to understand is in terms of entropy production, can we find bounds as to why P3 and P4 are outliers compared to P1 and P2? So far, I don't really have any physical insights on this, to be honest. But I mean, this fact is not a feature of the parameters we have chosen. In fact, we prove in the preprint that this holds quite general, as in any set of parameters we choose, this seems to hold anyway. Right now, I really don't have any insights as to why this should be the case.
Okay.
I'm sorry, again, I couldn't hear if you said something, but
No, I really don't know what to say as well.
okay.
I have one more question on your plot, where is on the useful probabilities. The next slide.
Is it
Yes, here.
this?
Yes. Do you know what gives the maximum in this plot?
So, so far, any higher pH by TC seem to have a bigger peak as well, but my guess is that it'll eventually fizzle out because the area under this curve should be equal to 1. I mean, probability of all useful cycles should be 1. But I don't have in terms of numbers as to what gives, or even, yeah,
Yes, it looks
analytically,
pretty close for all TS by TC. Like the maximum is always almost at the same gamma T.
yes. Max, okay, by that, okay, if you meant at what time, yes. It seems that the maximum is achieved at a particular time scale. And it's quite sad that there is any attempts at getting this analytically done was a failure because of the formulas being quite general, given that there are at least 7 parameters for this 3-level measure. But that's a good point. I'll have to check if for any other temperature ratios do I observe the maximum at the same gamma T.
Any questions over Zoom? Okay, if no further questions, let's thank Abhay.
Again, thanks for the opportunity. It was wonderful chatting with you all. Thank you.